Hello students, welcome to the Quick Solutions All India AIATS Test Series JEE Advanced 2020 Test 2A Paper 1 Physics. Let's go to question number 1. Question 1 says, a string of length 2 meter is fixed at both ends. It is vibrating in its second overtone with maximum amplitude of 2 millimeter. The amplitude at a distance of 1/6 meter from one end is. Well, it's a question based on standing waves in a string fixed at both ends, and it's given that the string is vibrating in second overtone. That means there are 3 loops forming in the string overall. So if I show the 3 loops, it will look like this. And this is L. That being the case, we can see that the total length L is equal to 3 times lambda by 2, because each loop will have length lambda by 2, which gives us the value of lambda as 2L by 3, and L is given as 2 meter, so that means lambda is 4 by 3 meter. Okay. So now we can write expression for amplitude of the standing wave as a function of distance x from, let's say, the left end. Okay, so the amplitude in terms of x as a function of x is equal to the maximum amplitude, which is 2 millimeter sine kx, or 2 pi by lambda into x. We can write here, we can check the boundary condition. At x equal to 0, amplitude is 0. We put the value of lambda and we get amplitude is 2 millimeter sine 2 pi lambda is 4 by 3, and the value of x is given in the question as 1/6. So this entire term is pi by 4. So we have amplitude is equal to 2 millimeter sine pi by 4. Sine pi by 4, and its value is clearly then √2 millimeter. Let's look at the options. Option C is matching with our answer, so option C is correct. Let's now go to the next question. Question 2 says the pressure of an ideal gas varies with volume as P is equal to P0 plus 1 minus alpha V square, where alpha greater than 1 is a constant. The pressure at which temperature attains its maximum value is. Well, the question is based on the ideal gas equation, and we can use that equation. So we have been given P is equal to P0 into plus 1 minus alpha V square. Now we have to get the pressure at which temperature attains its maximum value. So we can get an expression of P in terms of T. So we need to eliminate V. So we can eliminate V by using the equation PV is equal to nRT. So we can write V is equal to nRT by P, and so we get P is equal to then P0, which is a constant, plus 1 minus alpha. V square will become n square r square t square by p square. Or we can simplify further, and if we simplify it further, we get PQ is equal to P0 into p square. We can write here minus alpha minus 1, because alpha is greater than 1, into n square r square t square, which gives us t square is equal to P0 p square minus PQ divided by n square r square into alpha minus 1. When temperature attains its maximum value, T square will also attain its maximum value, and at maximum value of temperature, derivative of T square respect to P will be 0. So if I do that, if I find d by dp of T square and put it to 0, what do we get? So I am using this d by dp of T square equals 0, and which gives us 2P naught P minus 3P square equals 0, or the pressure itself is equal to 2P naught by 3. Let's look at the options. Option B matches with our answer. So option B is correct. Let's go to the next question now. Question 3 says, a parallel plate capacitor filled with a dielectric of dielectric constant K has capacitance C. It is charged to a potential V0. It is now disconnected from the cell and the dielectric slab is removed. It is now discharged through a resistor of resistance R starting at t equal to 0. Time instant when potential difference across capacitor becomes V0 by 2 is, we have to find the correct option. Well, we can see the question is based on the concept of capacitors and also a discharging RC circuit. We first find the charge on the capacitor. Now its capacitance is C and potential to which it is charged is V0. So the initial charge on the capacitor, we can call Q0, is equal to CV0, right? Now the capacitor has been disconnected from the cell and the dielectric slab has also been removed. So if the dielectric slab, whose dielectric constant is K, has been removed, the new capacitance C dash will become original capacitance divided by K, and which means the initial potential difference, the potential difference has now increased, and the new potential difference across the capacitor will be equal to the charge by C dash, and that means it is the new potential difference, let's call it V0 dash, is equal to Q0 by C dash, and if you put the value of C dash, it turns out to be equal to KV0. Now this is discharged through a resistance R. What is the time constant for the discharging circuit? Time constant is RC dash, and that means it is equal to RC by K, and the potential difference V can be written as V0 dash, the initial potential difference, the potential difference at t equal to 0 into e to the power minus t by tau, and the time constant is RC by K. So this is the expression. This potential difference becomes V0 by 2, and we also put the value of V0 dash. So we get the equation V0 by 2 equals KV0 e to the power minus tk upon RC. Solving, we get 2k equals e to the power tk upon RC. Take log on both sides, and we get ln 2k equals tk upon RC, which means the time at which this happens is equal to RC by K ln 2k. Let's look at the options. Option B is matching with our answer, so option B is correct. Let's go to the next question now. Question 4 says, find the equivalent resistance between points A and B. Well, obviously the question is from the section current electricity, and we have to find the equivalent resistance between 2 points. For doing this, we connect an ideal cell between points A and B and distribute the current in the circuit. So if we do that, we just connect an ideal cell and make use of whatever symmetry is there. The symmetry is there in this term, that this is 2 ohm and this is 3 ohm. Here it is 3 ohm and here it is 2 ohm. So if I assume that current in this 2 ohm is X and current in this 3 ohm is Y, then by symmetry current in this 3 ohm will be again Y, and here it will be X, and the total current in the circuit is X plus Y. Let's say EMF is V. If we apply the Kirchhoff junction rule at this junction, the current here in 1 ohm we can show in this direction to be X minus Y. So the current is now distributed, we can now apply Kirchhoff's voltage law or Kirchhoff's loop law. Let's first apply the loop law in this loop starting from this point, and the equation we get is minus 2x minus 1 into x minus y plus 3y equals 0, which on simplification gives us 3x equals 4y or y equals 3x by 4. Let's call it equation 1. What is the value of RAB? RAB is the potential difference between A and B and the total current that follows. So the expression that we are trying to find is RAB, which is equal to V upon x plus y. And since y is equal to 3x by 4, so we are effectively trying to find V upon x plus 3x by 4, which is equal to V into 4 divided by 7x. Let's apply the Kirchhoff's voltage law once again, including in the loop we'll include the cell also. So V is equal to, we get V is equal to 2x plus 3y, and if we substitute the value of y, we get it as 2x plus 3 into 3, that means 9x by 4 or 17x by 4. So RAB is now equal to V by x into 4 by 7 from here, and V by x is 17 by 4 ohm. So that means it is equal to 17 by 4 into 4 by 7, which gives us 17 by 7 ohm. Let's look at the options. So option D is correct. Let's now go to the next question. Question 5 says, a tapered rod of length L has cross-sectional radii A and B as shown in figure. Its thermal conductivity is K. If temperature at two ends are maintained at T1 and T2, then temperature at midpoint P of rod is, it's given T1 is greater than T2, and we have these 4 options. We have to find the temperature at the midpoint of the rod. Well, the idea is that we find an expression for the rate of heat flow through this tapered rod, and based on that we find its thermal resistance, and then we find thermal resistance of each half, P being the midpoint, so the left half and the right half, and then we find the temperature of point P. So to find the rate of heat flow, just go to x distance from left end. Suppose we are here, this distance is x, and we can see that the radius here r will be a function of x, and the expression for r will be then a plus b minus a by L into x. This is the expression for radius, which is a function of x. Now if I consider heat transfer through an element of thickness dx, then we can straightaway write the rate of heat flow H is equal to minus k area of cross section, which is in this case equal to pi into a plus b minus a by L into x square dt by dx, the temperature gradient. Now in steady state, the rate of heat flow is going to be same through every element. So in the next step, we write H dx divided by pi into a plus b minus a by L into x square is equal to minus k dt, and let's integrate. X goes from 0 to L and temperature goes from T1 to T2. So on the right hand side we will get k into T1 minus T2. On the left hand side, on integrating, we shall get h by pi, and integral of this will be equal to minus 1 divided by a plus b minus a by L into x and the limits of x go from 0 to L. And we also need to divide by the coefficient of x, which is b minus a by L. So that means we shall have here b minus a by L. And if we put the limits, we get it as LH by pi into b minus a. If we put x equal to L, then we are getting, then a gets cancelled. So considering the minus sign here, we are going to get here 1 by a minus 1 by b. So again, further simplifying the left hand side, we get LH by pi, and the b minus a will cancel. So here it is AB, and this is equal to K into T1 minus T2. So that means thermal resistance R, let's call it simply R, is equal to, we know that thermal resistance is T1 minus T2 divided by H, and in this case it is equal to L divided by pi K AB. So now we are in a position to find the resistance of this part. We can call it R1, and resistance of this part, which is R2, using the same expression. For the left part, value of A will be A, but value of B will be A plus B by 2. So that means we get R1 is equal to L divided by pi K A into A plus B divided by 2. And for the right half, the thermal resistance will be equal to L divided by pi K into A plus B by 2 into B. Also, to find the temperature at point P, let's connect the two thermal resistances in series. Here we have point P, and this is R1 and this is R2. This point has temperature T1, this point has temperature T2, and this is the rate of heat flow. So we get the expression, let's say the temperature here is Tp. So that means T1 minus Tp by R1 equals Tp minus T2 by R2. So using this equation and the expressions for R1 and R2, we will find that the temperature Tp comes out to be T1A plus T2B divided by A plus B, which matches with option D. So option D is correct for this question. Let's now go to the next question. Question 6 says, a point charge Q is located at the center of a ring of radius R with uniformly distributed charge minus Q. The magnitude of electric field at a point on axis of ring at distance D is, where D is much larger than R. Okay, so clearly the question is based on electrostatics, and we have to find electric field at this point at distance D from the center of the ring. So this is the point, let's call it P. The ring has minus Q charge uniformly distributed, right? It's a minus Q, and on at the center is point charge plus Q. So electric field at point P will obviously be found by vector addition of electric fields that the ring and the point charge will create at point P. So E at P will be, for the point charge, it is 1 by 4 pi epsilon naught Q by D square, and the field created by the ring will be in exactly opposite direction, and that field is 1 by 4 pi epsilon naught Q divided by R square plus D square to the power 3 by 2 into D. This is the expression for electric field at point P, found by superposing the electric field created by the point charge and the ring. Now we will use the condition that's been given, that D is much larger than R. This will give us the electric field at point P is equal to Q by 4 pi epsilon naught into 1 by D square. Here we can take D as a factor. So On the numerator we have d here, but here if we take d as a factor outside, so that means we'll have here dq, d square to the power 3 by 2 is dq, into 1 plus r square by d square to the power 3 by 2. And now we can use the binomial approximation here. So we get electric field at point P is equal to q by 4 pi epsilon naught 1 by d square minus again 1 by d square, and this is 1 plus r square by d square to the power minus 3 by 2, and that means it's equal to 1 minus 3 by 2 r square by d square. So we can see that this 1 by d square and this minus 1 by d square will cancel. This is equal to q by 4 pi epsilon naught 3 by 2 r square by d square, and there is one more d square here. So this is, so we can see on simplifying, the electric field at point P is equal to 3q r square divided by 8 pi epsilon naught d to the power 4. Let's look at the options now. We can see that it is matching with option C. So option C is correct. Let's now go to the next question.